Hi students and welcome to Chem 111. This short little video and PowerPoint presentation will be some supplementary or review information for Chapter 1. So we're going to cover Chapter 1 in class, but we won't necessarily cover everything. And so these are some of the topics we're not going to hit upon, but you'll still want to know for the test, but also just to know to do well in chemistry. So sit back and watch this video. So again, students, this is some extra material. Just know that the notes, the actual slides, are also available in e-learning on the class site as well. So we said in class that chemistry is a study of matter and the physical and chemical changes that matter undergoes. So let's think about some ways that we can categorize matter, some ways we can think about its properties. So we'll do these in sets. The first set of properties that we'll think about are its chemical and physical properties. And of course we can see that here, that in the physical property is something like density and color would be two examples. So we can see that the liquid on the bottom of this glass has the highest density, sinks to the bottom. This one in the middle, the next highest. And then the liquid on the very top has the lowest density, hence why it goes to the top. And of course, as you can see, another aspect of that is that these are all three different colors. And so that's another physical property. A chemical property is the fact that matter can react in some way, that it can change its nature. So this would be like an explosion, combustion as you see here, or even something like stainless steel where it has a lack of rusting. So stainless steel basically resists rusting, that is reacting in the presence of water, and that's a chemical property, that it's an inertness that also comes along. Alright, so two ways we can think about matter. We can also think about another set of properties of the intensive and extensive properties. And we can see that with this beaker here full of liquid. So an intensive property is something that is inherent to that particular matter, something like melting point or density. So what we mean by that is that water, whether you have just a little bit, say the cup full that you see here in the picture, the green liquid, which is basically water with food coloring, it would have the same density as if you had a whole swimming pool full of that. And so it's intensive. That's something about that property that makes it specific to that no matter the amount. All right? And so again, melting point, density would be two examples of something that's an intensive property. Extensive properties are things such as volume and mass, where it does matter how much of the material is there. And you might think of that and say, well, of course, I mean, that's self-evident that volume and mass are extensive properties, and it's true. But the point is, it's to show that there is a difference between the intensive and the extensive, that the intensive, it does not matter the amount of matter, whereas the extensive, it does indeed matter how much is there. So volume and mass would be examples of those. And we'll talk about intensive properties and extensive a little bit later on. When we see changes in matter, when we think about this, again, we can link those to our physical and chemical properties, and so talk about chemical and physical change. So again, if we think about a chemical change, as I said, it's when there's an explosion, decomposition, rusting, something along those lines. That would be a change in the composition. So we're starting off with one type of matter. Say if something burns, that's typically a carbon-based, and it's burning and it becomes carbon dioxide and water. All right, so those are chemical changes. And so again, we can always think about the verbs that we're using when we're describing these changes. Exploding, decomposing, rusting, that all sort of indicates a change in the chemical state of those. Physical change is really just a change of state, where we're melting, say, ice. So ice goes from solid to liquid. That would just be a physical change. It's still water. The identity of the substance hasn't changed. But this would also be true if we're just cutting substance. So you take a tree and cut it, so you take a nut and you break it in half. Something along those lines would be examples of a physical change that's taking place. Oftentimes we'll take types of matter and we'll mix them together to make a mixture. And sometimes we'll need to separate those mixtures. And one way that we can separate a mixture, as we see in this video, is through a chemical reaction. So we have a clear liquid initially. We added some reagent to it. Notice we got a white precipitate, that is a white solid that formed, and after we let that solid settle for a while, then you can see that there's a white solid more on the bottom, and then there's a clear liquid above it. All right, and so again, preferentially what we did in this case is that, again, we had a liquid mixture of two types of matter at least. We added a reagent that would react with one, but not the other. And so the result of that was a solid, and now we have a solid-liquid mixture, which is easier to separate than when you have two things that are liquids. We're going to see some examples of this next week in Laboratory 2, where we use chemical reactions. We're also going to see an example of what happens when you create a solid liquid, as we've just done. How do we separate those? And this is actually through filtration. And so again, we can see in our little video that's coming up that if we have this solid liquid mixture, and our student, she's swirling it around to mix up the solid liquid, and we're dumping it into a filter, which contains a piece of filter paper, and the piece of filter paper would be right in here. And as basically the vacuum pulls the liquid through this piece of filter paper, the solid remains behind, and in the filter, and then the liquid's pulled through. And then our student, she left the beaker, the initial material there to the right, and you can see that we've effectively separated the liquid, which you can see in the bottom, it's clear, and then a white solid, which is left in the filter paper. So this is a fantastic way to really separate a solid liquid. We're going to use this again in lab next week. Well, what happens if we have two liquids? They're not as easy to separate, so we can use a process known as distillation. All right? And so in distillation, what happens is that we can take a liquid mixture. In this case, if you look in our diet, it's basically salt water. So we have salt and water. And so let's say we just wanted the water by itself. Well, we could heat that with a Bunsen burner, which you see down here. And that would heat the liquid. The liquid water would actually boil. The salt is non-volatile. That means it doesn't boil. And so then the liquid water would come up here, and then as a gas phase, and then move down into the condenser. And the condenser basically has cold water, which would cool it, and then it would reform water, and then finally it would drip down into the flask here. All right, so we would collect it in the receiving flask. And so we would actually be able to separate then effectively the water from the salt. The salt would be left behind in the boiling flask. All right, so this is known as distillation, and this is what happens when they make alcohol. You've heard about a distillery, and that's really just the place where they make alcohol. So they mix together some reagents to make alcohol, and then they want to, of course, separate it from the mixture, and they do that by really the same process. And then sometimes we can work with something known as chromatography, a way to separate various compounds. Maybe you've done this at home with a magic marker and water, or magic marker and alcohol, depending on the type of marker. And basically what happens, if you know, is that we have a medium, which in this case is just a piece of filter paper. And we basically put a dot, as you can see there, a black dot on the very left, right over here, on the piece of filter paper. And we dip it into water. We don't want to, into the bottom of the paper, and then the water, or the liquid in this way, moves up. Right? And as it moves up, trying to make a nice arrow. As it moves up, what happens is that it starts to separate the various dyes. All right, and so you can see that here in the middle, I should say, we can actually see those dyes that are separating. And then over here on the end, as the water continues to move up, the dyes are separating. And this is known as chromatography. And this chromatography is a way that we use to separate various compounds, such as various dyes or other things. And it's typically used in analytical work, so to analyze environmental samples or something along those lines. All right, so of these techniques, we'll mostly use A and B, chemical reactions and filtrations, this semester in lab. The distillation and chromatography, won't occur until later chemistry classes, organic chemistry primarily. But just know that there are ways to separate mixtures. As we move from matter, we need to think about, all right, for separating matter, we need a way to measure those. Measure the volume, measure the mass, and this is where we come into our units of measure. All right, so the units that we use primarily in lab are the SI units. All right, so the System International units, and this is French, so that's why it sort of seems backwards to us, the System International units, but it's the SI, it's French. This convention came about in 1960, and it was a way to globally have everybody using the same units when we make measurements in lab. Now this is in the United States, of course. We use these in the laboratory, everyday use, such as for woodworking and for shop and those types of things. We tend to use the English units still, one of the few countries that still do that. But nonetheless, in the countries around the world, not only do they use it in science, but in everyday life, buying a gallon of milk, but they would buy liters of milk. So they tend to use just in everyday life. A couple of things, the SI units, there are 7 base units. I'll show you those on the next slide, such as the kilogram and the meter, and also some prefixes, and you want to memorize both of these. I'm not an advocate of lots of memorization, but these 2 tables that we'll see here are things that you really should memorize, and you should know those. Just they'll help you do better in science in general. All right, so let's take a look at table 1.4. These are the base units. All right, so there are 7 base units that we use for things, as we can see here, mass and length and those things to separate out. You want to know the names of the units, what the units are, and what their abbreviation. As an example, we often think about mass as having a base unit of gram, because that would seem to fit everything else. There's no kilos or millis or anything else in this list, but just note that the base unit for mass is kilogram. The reason is the gram is a fairly tiny unit, not really meaningful for everyday work in the lab, but a kilogram would be much more meaningful. So that's one where students sort of often trip themselves up in thinking about the gram. And then you'll notice the others are pretty common, length and time. One of the ones you may not be too familiar with is luminosity, and that unit is candela, and it's abbreviated as CD, as you see there. And this is actually used occasionally. I saw an article in the Pittsburgh newspaper a couple years ago, and they were talking about the Grant Tower, which is one of the buildings in downtown Pittsburgh, and it has a light on top of it for protection, to let airplanes know that there's a building that's that tall. And they pointed out that the light on that tower has a luminosity of 3.25 million candela light, or candela. And that was one of the few times in just sort of normal everyday discourse I saw candela. And just FYI, that tower with the 3.25 million candela can be seen from 75 to 125 miles away by an airplane. All right, so it's good for them. All right, so know those 7 units. Also know the prefixes are in this table 1.5, so everything from the penta down to the zepto. So you want to know what the prefix are, something like tetra or giga. Also know its 1-letter abbreviation, the T, or the T for tera, G for giga. And then also know the meaning of those in terms of 10 to the 12th, whatever it would be. And then notice that in this last column that it shows you an example. All right, so this last one is just an example. So 1 petawatt is equal to 1 times 10 to the 15 watts. And that's just that, and it's an example for you. And so you want to use those, and it's also a good way to think about conversion factors, which we'll talk about in just a little bit. A couple of things about using SI units. Again, and when we often talk about units, we'll talk about them in terms of plural because we'll have multiple ones. But we always want to use the milligrams and not put an S on there. Even if it's 151.6 milligrams, we're still just going to use the singular one. Also in English, we tend to use periods to abbreviate. We're not going to do that. We're just going to use the milligram. All right, so to prove that. And then also, key thing is we want to know that the upper and lowercase are very different. A milligram, lowercase mg, is not equal to a megagram, capital MG. So that's very just important to know those. Temperatures, know that there are 3 types of temperature that we'll talk about in class. One's Fahrenheit, is our normal temperature that we think about in our daily lives. Celsius temperature is the one that we typically measure in the laboratory. All right, so most of our thermometers are Celsius only. And then the last one is Kelvin, and the Kelvin is the unit that we use when we do calculations, because Kelvin is an absolute temperature scale. Fahrenheit and Celsius are both dependent upon the freezing point and the boiling point of water. All right, so when we do calculations, we must always use Kelvin because it's an absolute scale. You will not need to memorize these mathematical formulas, which are shown here. All right, so these guys, you will not need to memorize those, but you will need to know how to use them. And so to be able to convert from Fahrenheit to Celsius, given this formula, convert into Kelvin using the formula that's given here. And that'll just help you. But just know that especially when we start to do gas laws and we use a lot of Kelvin, we're always going to use that unit of Kelvin. One of the things that our calculators will do quite quickly for us is to put numbers into scientific notation. We can even program a calculator just to do it automatically. But you also want to make sure you know how to do this by hand, just to understand it. So we're going to show you 2 examples of working with scientific notation. These 2 numbers right here, taking 25,000, converting it into 2.5 times 10 to the 4th, and taking this small number, 0.0031, and converting that into 3.1 times 10 to the minus 3. So as we do that, we'll see, of course, the first thing that we want to do is we want to move the decimal place to get a number between 1 and 9. All right, so standard, we take 25,000. Here we would actually then move the decimal from the understood here all the way over to there. And so that gives us this number. And we would do the same thing with the 3.1. All right, to get 3.1. And that's the most standard way to put a number, is a number between 1 and 9. Then, of course, we just multiply that number by 10 because that's going to be the standard. And then finally, we want to think about how many places we move the decimal. So when we move the decimal rightward, then the exponent is negative. As we see here in this 3.1 times 10 to the minus 3, we moved it 3 spaces to the right. And so that got us negative 3. And then the 25,000, again, we moved it 4 places to the left, and that has a positive value. All right, so that's how we put numbers in scientific notation, and we just want to be able to remember that. Also, when we make measurements in lab, there's always a bit of uncertainty that comes with those. And so we have 2 ways to talk about that uncertainty. One of them is precision. And precision, the exact definition of that is a measure of how closely individual measurements agree with one another. It's how close they are. In our little target analogy here, we can see that this dart throwing was very precise. All 3 of those darts are very close together. And also, those 3 darts are very close together. So we would say that those first two sets have very good precision, all right, because the person throwing them was able to throw them in the same way and get the darts really close together. What we're talking about in lab is that a balance or an individual is able to measure something, and that those measurements are very close together. All right, it has good precision. Accuracy is a little bit different, and accuracy is defined as how closely individual measurements agree with the correct or true values. All right, so what we can see is that in this top one, again, it has good accuracy because the true value or the true target was the middle. All right, so this one has good accuracy, and this one has bad accuracy, poor accuracy as it says, because the darts were not on target. All right, so we wanted them right in there, and they didn't quite get there. All right, and so of course then the bottom one, it has both poor accuracy and poor precision. So we want to make sure we know the difference between them. Precise is, again, how easily and how well measurements agree with one another, and then accuracy is there a given target, and how close did we come to a given target? So in the laboratory, there might be the density of water might be accepted to be a certain value at, say, 27 degrees. All right, and so when we measure that in the laboratory, how accurate or how close to that true or accepted value that someone else did do we actually come close to that? Did we come close to that? And then finally, I just want to end with dimensional analysis, which we will do 2 days in class, but this is such an important part of chemistry, doing calculations, that I thought I would just put a little blurb here. And again, on this first calculation, we see that we're going to convert 10.5 pounds to grams. How do we do that? Well, there's this little scheme. I like these little schemes in your book to show you how to do that. All right, now it's very simplistic in this first one, but the idea is that you're given pounds, you want to get a grams. What do you use? Well, you use this conversion factor right here. Right, and so you do that by plugging it in to this type of calculation. And so we're going to use this sort of manner of calculation where we have sort of our given value, we have this conversion factor, and then the answer. You may have learned to do it a little bit differently. Sometimes you might cross multiply, sometimes you might set it up. You have to have a systematic way of doing that. And oftentimes for chemistry, especially when we start doing multi-step calculations, it'll be best to do it this way. So you need to make sure that you can show your work to someone else who is grading it or is looking at it. All right, just doing it in your head or scribbling on a piece of paper is not good enough for the way we're going to do things academically here, because we're ultimately training you to be scientists and engineers, and you're going to have to communicate this information to other people that are oftentimes scientists or engineers, and they need to be able to follow your work. All right, and so again, what we see here is that we have done this calculation, and we again notice that we've set it up so that the pounds are, when we multiply through, 1 pounds on top, the other one's on bottom, and so those cancel out, and we're left with just grams. And then, of course, noticing that we end up, if you put it in your calculator, with 4,762.8 grams. Of course, that has too many significant figures, as we learned in class. So we need to round that and use scientific notation, and here we end up with 4.76 times 10 to the third grams. All right, so that's just our first conversion. And then I just show an example, again, using a little scheme from your textbook. When you use 2 or more conversion factors, and so if you want to convert from meters to inches, one way to do that is to convert from meters first to centimeters, using that relationship of 1 centimeter is equal to 10 to the minus second meters and centimeters, and then use a second conversion factor of 1 inch is equal to 2.54 centimeters exactly, and converting that into inches. All right, and so so we're going to be working more with dimensional analysis, but just make sure that you're comfortable with working with numbers and doing calculations. Do some additional homework, and of course then there's the quizzes and the homework, which are also going to help you with this. So again, these notes, just the sort of notes that you can download, are available in the e-learning course to accompany this little video.